We are recording. Sorry, I'm running a little bit behind. Come on. Okay, so today we are going to talk about so we have been kind of solidly in the prediction realm, right? And we took a little detour quickly to talk about some clustering algorithms, but we're going to move back to thinking about predictive models. We're going to start straying into kind of the territory of I guess what we would call some more classic machine learning models, but I mean they're all just regressions at the end of the day. Specifically, what we talked about with splines and kernel regressions had mainly been focused on thinking about non-linear functional fits, right? But in sort of continuous territory, okay? And so kind of analogous to how we thought about in kind of the linear regression area, linear regression and logistic regression. Today we're going to talk about some classification methods in machine learning, simple machine learning, right? And so this means dealing with outcome variables where your y is discrete, okay? So let's get started here. Okay, so the first thing, the first concept I'm going to introduce to talk about is something known as a hyperplane. So the definition of a hyperplane is a flat, affine surface. It's not surface, subspace. Of dimension p minus 1 in p-dimensional space. Okay, so here is a pretty simple example of this. We have x1 and x2. And so the idea here is if you think of x1 and x2 as your data, and then these data points here, blue being one of the discrete outcomes of your y and red being the other one, I can actually draw something like this. So this would be a hyperplane. And this hyperplane acts to separate these spaces, right? And so if we think about this from a classification point of view, I could basically say, well, on one side of the hyperplane, I can predict that all the points are going to be blue, and on the other side of the hyperplane, predict that all of the points are going to be red, right? And so pretty simple example of this sort of application. We're thinking about this in kind of like a different manner, right? But hopefully this is a sort of pretty logical model for you guys. So in 2 dimensions, you might have something like this that defines the hyperplane. E2 x2 equals 0 in 2D. And then more generically, in p dimensions, we might have something that looks like this. Beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth. Beta p xp equals 0. Okay, so this is kind of the concept that we're going to be building up when we talk about figuring out how to do some kind of classification system. Okay, any questions about this? Yep, pretty straightforward. Okay, so we're going to start off with a particular type of classifier. This is going to be called the maximal margin classifier. And so this would be an optimal separating hyperplane. So this would be a separating hyperplane that is farthest from training observations. So this part right here at the back, that's a pretty important concept to think about. And so why is that? So let's think about an example here. I'm going to draw another sort of red dot, blue dot type thing here. We'll have x1, x2, and I'm going to draw a couple of points here, and let's say a couple of points over here. Okay, so question for you guys. Would this line here be considered a separating hyperplane? Yes. Okay, what about this one? Yes. What about this one? Yeah, and so in fact, I could do this for all of eternity because there are actually an infinite number of hyperplanes that would separate these points, right? So infinite number of separating hyperplanes. So we need something to help us figure out kind of one single hyperplane that we can land on. And the way that they do this is via this thing right at the end, farthest from training observations. And so what I'm going to do here is I'm going to take my same thing here. Let me add my points back in. And the idea is I want to draw a line right, that is farthest from my training observations. And what that means is you draw some kind of line here, and you want essentially, if you think of orthogonal distances to that line, like so. This distance here is known as a support vector. I think the reason why it's called a support vector, it's been described to me as like, if you think of these support vectors as kind of like pillars that are holding, or that are like supporting the line in place. That's kind of one description that you can use. That's what was described to me, right? So these these sort of pillars, and you want essentially to maximize the size of your support vectors. And that will let you converge to a single separating hyperplane that will separate these classifiers. So I'll write down the kind of math behind this, or kind of of this particular optimization. But again, that's just for reference. We don't really need to deal with how this actually works. But the idea is we want to maximize our margin classifier subject to our parameters. Such that the sum j equals 1, p beta j squared equals 1, with a constraint that yi times beta 0 plus beta 1 xi1 plus beta 2 xi2 beta p xip is greater than or equal to m for all I equals 1 through n. Okay. So this constraint maintains this hyperplane that is constrained to sort of exactly separate your outcomes, and do so in a way that maximizes the size of the support vectors. So that's kind of the main concept here. Okay, so what are some problems with the maximal margin classifier? What do you guys think? Yeah.
It only allows for kind of binary classification. Either on one side or the other.
Yes. Yeah. So not. I see what you're saying. Yes, it is. The only caveat that I would say, so you're exactly right. We call this something slightly different. It's non-separable as opposed to binary, because this classifier could actually deal with like more than two outcomes. So it's technically not binary, but it's not separable, which is what you're implying.
What does not separable?
Yeah. I'll show you in a second. So two issues. One is non-separable. Cases don't work. So if I have this, okay. And this is very common, right? So who can tell me a hyperplane that will separate your outcomes perfectly? You can't, right? It's actually not possible. So this would break your classifier. And so I think this is what, Christopher, you were kind of referring to, is that that you can actually cleanly separate these things. Is that right?
No. I mean, this is a good insight, but what I was referring to, it seems that at least in 2D, or I don't know, 3D, a plane has two sides. Does a plane have more than two sides when you go into higher dimensions? That's how I see the hyperplane working as a classification tool. Is like your data is either on one side of the domain or the other.
I see. the hyperplane. Actually, is that right? I was thinking in 3D space. Yeah, you're.
Just change the plane so this way you have your y. That x doesn't necessarily mean that it's on the same plane. It could be the y axis going up or on the z going up, right?
Yeah, no, but I actually wait. Yeah, no, actually, I think you're actually right. I confused myself for a second. It's actually so you can do you can have more than two input variables, but the outcome is binary. Yes. Yeah, sorry for that mistake. I actually have not thought about it in that way in a while. So the idea is that you could do it in like 3D space, but you would still have like a 2D plane that would be separating two different outcomes. So we're going to actually see other classifiers which you could actually do more than two types of outcomes. And the way they do that is the hyperplane becomes like nonlinear, and you can like make folds. But that's a pretty, I would say that's a less common use case for this type of thing. I guess I do usually think of these as like focused on binary variables, binary outcomes. Yeah. Okay. So back to the maximal margin classifier. Non-separable cases is one particular issue where you simply would not have the ability to create a classifier using the maximal margin case. And the second issue is that even if you do, even if the points are easily separable, you have very high sensitivity to individual observations. So let's see here. If I were to draw a hyperplane here, that might look something like this, with my support vectors like so. But if I were to modify my data just a little bit, so let me try and replicate this. Okay. And I have something here. And let's say I drew a point like here. So then, where the old point was here, right, and my previous hyperplane might be something like this. Now that's migrated or shifted the line quite a bit just by moving a single point from here down to here, right? And so the basic idea is that individual observations, right, even a single observation can push the entire hyperplane in a certain direction because the hyperplane has to be maintaining this rule of separability, okay? And so this particular model, even in separable cases, is like very, very susceptible to like outliers. Okay, so how do we deal with that? So the second model that we'll talk about is the support vector classifier. And so this was really kind of an evolution of our MMC, our maximum margin classifier. It has general robustness to individual observations. And better classification of most training observations. So it's the same optimization as the MMC, but with an additional constraint. And the idea here is you have this thing, sum of I equals 1 to n, epsilon I less than or equal to c. So this is a tuning parameter. And essentially what that does, so let me write out our constraint, yi beta 0 plus beta 1 xi1 plus beta 2 xi2, so on, beta p xip is greater than or equal to m times 1 minus epsilon I. So this is our slack variable. Okay, so what's going on here? We have a few things. One parameter, epsilon I, tells us how many points can violate the margin, right? So the idea here is that when we put our classifier, our hyperplane classifier down, it is not perfectly separable because we've allowed for some slack to happen, which is basically, okay, you're allowed to actually have, you know, a red point in the blue area, right, or a blue point in the red area, and I can allow some number of violations based on my epsilon, right? And so the trick is that you have this C tuning parameter. So this bounds the number of epsilon i's. So this is essentially like a budget for violations, right? And if you have C equals 0, it's the same as the MMC. Okay. So in the previous examples, basically you can re-accommodate some of those issues particularly thinking about the separability issue by giving this like flexibility of allowing some number of points to be violating our margin. Okay? Any questions about this? Yeah.
How common is a situation where you classify a data set and there's like only two outcomes you wish to classify them into? It just seems a little limited.
No,
For us, but
I mean, binary outcomes is a very common, it's a, yeah, actually pretty common type of analysis that you could do, which I guess is, part of one of the reasons why these things exist, because they're actually particularly efficient at modeling these outcomes.
okay.
Okay. And so in some cases, so this solves the non-separability thing, and then in some ways it also helps with the sensitivity argument, right? Because to some degree you can just allow for a point to violate the margin as opposed to trying to accommodate it by massively changing your hyperplane. The one kind of drawback of this particular thing, so issues remaining, is that it must be a linear separator. Okay? And so we've gone from the maximum margin classifier, from that to the support vector classifier. And then from here, kind of the next logical step to address this particular issue is essentially to make it so that the separator can be nonlinear. Okay? And so for my next trick, we're going to look at a support vector machine, or SVM. So if you have heard of support vector machines, SVMs, right? These are kind of the very commonly used machine learning tool for binary classifications, binary outcome classifications. And we've kind of arrived at thinking about this model from building up from the sort of basic MMC to the support vector classifier to this SVM. And so how can we do this? So we could allow for polynomial expansion or interactions of x's, but this explodes in size very quickly. So instead, we can modify and generalize computation of the support vector classifier. And the way this is done, so SVC uses a linear kernel, and SVMs can employ more complex kernels.
Where you put, instead we can modify and generalize the computation of
Oh,
the
sorry. Of the SVC.
Is that the previous tool we looked at?
Yep. So that is the support vector classifier. Okay, so what is the SVM actually doing? All it does is it's actually turning this into kind of a local regression problem, right? And so if you guys remember, where in a kernel regression, we now are looking at these algorithms that base predictions off of a bandwidth, which looks at points nearby, and it's making decisions about how to shape the your like regression line essentially based on proximity of points that are close by, right? And so with the support vector machine, we're doing exactly the same thing. Instead of a linear kernel that's just a straight line, I am looking based off of certain distances and using something similar to our local regression algorithms that we talked about with the kernel regressions applied here, and the common kernels that they use. So these are different from the ones that we talked about, right? Like the box kernel in the Gaussian kernel. These ones use polynomial and radial kernels. We don't need to get into the details of exactly how that works, right? But it's essentially doing these like local regressions to essentially allow our classifier to be sort of curved. And so now you are dealing with a problem that is able to do these, to create this separator and not only make it nonlinear, but also think about how to balance that against points that are classified in kind of the opposite space, right? And so if you have a bunch of red points, you could still have a blue point in there that you think is like, let's say it's too hard to try and get a classifier in there. And so for example, where was I? Like here, technically using a support vector machine, I might be able to do something like this, right? But maybe when you do your validation, right, that is altering the parameters of my hyperplane to allow me to do that. Maybe when you're doing the like cross-validation type of thing, that it would actually prefer a different hyperplane separator, maybe like that instead. Okay.
Cross-validation work for this?
Yeah, so it's very much akin to the same thing that it would do in all of the other sort of regression approaches that we've been taking, which is the validation procedures are basically playing with the values of your parameters that determine what this line looks like, right? And it's doing it in such a way to, in this case, it's going to try and maximize your support vectors, right? But in like the regressions, it's doing it in a way that is trying to reduce or find the balance between bias and variance, right? And so it's very much the same thing here. I'm altering my parameters to find the balance between bias and variance. So I'm trying to draw a classifier that's determined by messing with the values of my parameter to draw a line that will try and maximize my support vectors, reduce the number of violations, but also minimize the amount of like variance from my like out of sample predictions as much as possible. Okay. Any other questions? Okay. So let's take a look at this in R. So we'll need a couple of libraries. So E1071. And then there's a data set that we'll use for our SVM, that you can find on Canvas. Okay, so we're going to start with the support vector classifier example. And actually, I'm going to set a seed here so that everyone can have the same results. Since these things are sensitive. Okay, and all I'm doing right now is building out my my data set. This is not the one we're using an external data set yet. Okay, so kind of same thing as before, right? Where I have my blue points and my red points. The color is the two outcomes of my response variable, and I want to be able to essentially draw a hyperplane here under the support vector classifier. All right, so we'll do so remember, a support vector classifier is actually just a support vector machine where the kernel is linear. And so what we're going to do is we're going to use this function called SVM, which is support vector machine. We'll do y on x1 and x2, which I do representing as a period. Data equals dat. Actually, if we want, we can look at the data really quick. U dat. Oh, I didn't run it. Okay, and so we have our y, our v1, and our v2, and so that's just x1 and x2, and you can see all of the sort of data points. And the y, if it's -1, it's red, and if it's positive 1, it's blue. Okay? So kernel, we're going to choose a linear kernel. Cost is 10. Scale false. Okay, so when I run this and I run summary, it'll tell me a little bit about what's going on here. So here we're using a linear kernel, cost of 10, that's our big C. That's, I believe, the budget for the number of violations. This will choose a total of 6 support vectors across our 2 classes. Okay. And, oops. Let's plot SVM fit. Okay. What was that?
Why does it have this like weird shape in the middle?
Oh, that's just like an artifact of the lower lower resolution, like drawing of a line, basically. Yes.
I have number of support vectors to be 7. What could potentially be wrong?
Are you using set seed? So here?
Yes.
Is anyone else getting 7?
I'm getting, could not find function SVM.
Ah, that's because you need library E1071.
Yeah, I got no package is called.
Is anyone else having that issue?
Is it like a specific package?
Yeah, it should be.
Called E1071?
Yeah. Okay, I'll help you in just a second. Okay, that would be strange if we're using the same seed. I'm not sure. Maybe I'll take a look in a second for you as well. Okay, so what is going on here? So it has drawn a hyperplane for us, and then the classification, right? It's saying everything here should be a value of -1, and everything up here should be a value of 1. And then the x's here indicate our support vector. Okay. You'll also notice that there are some violations based on the color of the points. So black should be on one side and red on the other side. And so you actually do see a black point here and a red point here. And so that means that you've got 2 violations in our budget of 10. But it's preferring this as kind of our best technical. Okay? Did you?
I fixed it.
You fixed it.
Yeah, but I'm getting not this. I got number of supporting vectors is 11, and number 11. Yes.
Are you doing set seed?
Yeah.
Why would that be happening?
I also didn't get that graph either for sure.
I did run set seed. Okay, we'll take a look in a second. In the meantime, let's continue on with the support vector machine example.
With the cost of 0, it would probably break with this data set, right?
If what?
If you have no violations, then it would probably break, right?
If you have
Allow no violations.
for the cost, yeah. So let's see what happens. Actually, that's a good.
So I fixed it.
You did. Okay.
So C was typed into but not run.
Ah, yes. Yes, that would not work. So you get an error. I wonder if it's possible. I actually think it is possible to build a hyperplane with 1, and I think it would look different. Can I run decimals? What do you mean?
Because you cannot run 0, right?
Yeah.
If you run like something greater.
No, because it's a number of, it's like a discrete number of violations. Yeah. Why is this happening? I'm actually not sure. Because this would indicate that there's 3 violations. All right, 1 second. Help SVM. So if we look at cost, okay. It's because the loss function size of epsilon. So actually, you're right. You could actually do. You could actually do a non-discrete value for your cost function because it depends on the size of a violation loss determined by epsilon, which I had been thinking of just as equal to 1, but apparently you can have a loss function that's, I mean, there's no reason why you couldn't, I guess, but the loss function doesn't have to be a discrete number. In this case, it's actually 0.1, and so, yeah, that's why this actually allows for more.
So you're reducing the sort of penalty for violation when you go from cost 10 to cost 1.
So I actually thought that the cost would be the budget that you're working with, but maybe I'm, okay, hang on. Do I have it backwards? Oh no.
Cost of constraint violation.
So cost of constraint violation.
Yes, that basically means, like if you have ISE, violations words, I guess.
Yeah.
Talk about the number of violations.
So that would not be the C that I'm thinking of then. But yes, this is basically telling us oh, it is the C constant. Okay, I must be thinking of this slightly differently.
But then if the C is 0, then that would mean that the cost of violation is 0. Right, so it's not the same as the one where you can have violation.
Yeah. So in the support vector classifier, the tuning parameter is the there is a constraint that forces your regularization constant to be greater than or equal to our loss function piece, right? So the epsilon. So because the default is at 0.1, if it's smaller than 0.1, it just wouldn't work, right? It would automatically violate the constraint. So, yeah. Okay. So I guess what is happening here is the relation of the tuning parameter is like telling us something about both the sort of budget for our epsilon, but it's also but it's kind of bounding the size of the penalty that you're allowed to have, right? And so setting it smaller makes it so that you're essentially allowed to have less violations, and then changing the epsilon is going to be how severe we penalize the violations.
I guess it's the other way around, if you make it big, then you can have less many violations because the cost is high.
So if you have,
Because the cost is like a penalty for one violation. A high cost would mean higher penalties for violations, which would mean less violations, right?
no. So the C basically tells us it's telling us a budget for the number of violations, right? So the larger C is, the more violations you're allowed to have. And then epsilon is, if you change epsilon to be large, that will use up more of your budget more quickly. Does that make sense? So if I do, so let's see. If I do cost equals so if I leave it at cost equals 1, but I change epsilon to be equal to 1, wait. It's not doing what I think it should be doing. Okay.
The default of epsilon is 1.
There's 0.1. So what it should be doing is that at an epsilon of 1 is it uses up the entire budget immediately as soon as you have a single violation. So it should allow for 1 violation, but
Can we try a really high cost?
I think we should try really.
yeah, oh, okay. I'm sorry guys, I don't know why this is happening like this. Okay. So the thing is, at a certain point, changing your budget to be really large will converge to something that because you don't need to, once you have a large enough budget, you'll always arrive at the same classifier, right? Because it will have maximized my support vectors. And so I would imagine that at 100 versus at a cost of 50, this shouldn't change very much. Yeah, and it's basically the same. The question is, the part where it starts to get interesting is where you're close to the budget, and now your hyperplane starts to become a little bit more sensitive. So I'm misinterpreting something about what exactly the function is doing to your cost and epsilon. But at the end of the day, right, essentially what's happening is it is allowing for some amount of flexibility in the generation of your hyperplane. And so how do I know what's the right cost and epsilon parameter values to set? Yay, cross-validation, yeah. So right, anytime we have flexibility in our model, what we want to fall back to is being able to predict as accurately as possible, right? And leverage the flexibility to give us the best out of sample predictions that we can. And so there are procedures in which you can alter the parameters here, right? There's two parameters that you can essentially mess with, which is your tuning parameter, your C and your epsilon, your cost and your epsilon. And when you do that, that'll give you the flexibility to change your hyperplane to kind of, reduce your errors as much as possible. Okay. So sorry about the confusion there. I'll try and look into what's going on with these costs and epsilons. Okay, so the next thing that we're going to do is to do the next example, which is a support vector machine, right? Which means that we can do non-linear hyperplanes. So I'm going to load in the data. Okay, so I'm going to remove X and Y and attach ESL mixture. Okay, so let's do a plot.
What's a RDA
Huh?
file? What's a RDA file?
On Canvas.
Yeah, so that file is on Canvas.
What
Oh, that's a type of data file in R, basically. Yeah.
How is that different from the typical CSV and
It's just saved in like an R-based format, basically, yeah. Okay, so here we have x1 and x2, and we have a particularly sort of messy plot, okay? And let's do this. So here we're going to do our SVM. And this time we're going to do radial, cost of 5. Gotta actually run this. So in here we have 103 support vectors across our two classes. Okay. And here we can see how the support vector machine has drawn our separating classifier, right? And saying basically everything here should be 0 and everything here should be 1. Obviously there's like a large number of violations happening, but this is kind of the one that will maximize our support vectors, given the set of data, right? And so this is, so SVMs are like a very powerful sort of way to do these nonlinear hyperplanes via some of this like local regression approach that we talked about previously, that allows us to do these sort of classifications. And then again, right, the parameters that we would mess with, such as cost and epsilon, those are the things that you might kind of play around with in order to get a classifier that will best provide predictions that reduce your MSE as much as possible. Okay. Okay, any questions? Yeah.
Is there like a good number to set costs to? Or, cause like I know that defaults to 1, so is that like just like a good benchmark there? Or like is there a reason why we always set it to a different value outside of its default value?
It's a little bit context dependent, right? Because it depends on the size of your data set and how much non-separability you observe in the data. Because
So like here there's a lot of
yeah,
ability, so will we then put the cost higher?
yes, yeah, exactly.
Sorry, could you repeat that again?
Huh?
Could you repeat that again?
Yeah, so it's not so easily generalizable to think about what the cost value should be set at, but the general rule of thumb is the larger the data set and the less separable the data are, which means like if you see a lot of like data overlapping, then generally you want to set the C value to be higher. Yeah, which allows you to have more violations. Yeah.
So like what, like as simple as you can like put it, like what is the difference between this and k-means clustering?
Yeah.
And what would, like, what are the different applications?
Yep. So they are both like very much sort of non-parametric approaches to do classification. They do it very differently, right? Or the approach behind how it does the classifications are quite different. With k-means clustering, you can actually separate into many different like discrete outcomes, right? Because it's based on however sort of many groups that you want. Whereas here, you know, we're mainly focused on in this particular case, 2 separating outcomes. And then as far as performance, actually, I've never really compared the two. It might be actually interesting to do like a quick.
They do also different things, right? Because this actually predicts something and the clustering just like parses into different clusters, right?
Oh, yeah, sorry. Not k-means. Are you talking about k and n? Or are you talking about k-means?
We were talking about last.
Oh, yeah. Okay, sorry. Everything I was talking about, I was thinking about in reference to k nearest neighbors as like a non-parametric classifier. So k-means is different. So the stuff that we talked about in the last lecture, so k-means, hierarchical clustering, and dbScan, that is unsupervised learning. So that is like a completely different kind of set of tools that is focused on exploring the data without knowing anything about a response variable. Whereas classifiers are specifically dealing with a subset of supervised learning where we care about discrete outcomes, right? Yeah, but maybe to kind of rework your original question, as it relates to k nearest neighbors as a non-parametric classifier, that is, yeah, in some ways similar to this. It allows you to create these like really weird boundaries, and in fact allows you to do classifications across multiple outcomes. Yeah, and I guess I don't really know about how the performance differs between like SVM and KNN, and in what context people use them. But I can look into that. Yeah. Yes.
So I noticed you, like, when you changed the cost value for SVM, for SVM fit.
Yeah.
Some of the X's turn into O's, and O's turn into the X's. What causes that?
Is that? Oh, maybe I'm just misinterpreting the the output plot. Maybe that's what it is. Okay, let's take a quick look.
So like I set it to like 10.
But it makes sense really, because the X's just indicate vectors, right? That are used. Support vectors. So the support vectors, so if you change your cost, the support vectors will be different, right?
Yes.
It might choose different ones.
Yeah, that's right. That's right. Yes. So my interpretation of the plot, which now I'm like so confused that it might be wrong, but my interpretation of the plot is that the X's are your support vectors, and then the O's are just other points, and then the classifications are broken down into like black and red. So it would make sense that X's changes to O's as your hyperplane changes shape, right? Because different points could act as the support vector.
So what is 0 and 1 then?
0 and 1 are just the values of y, and so this would be, this is basically saying, okay, so the way we interpret this is we've drawn a hyperplane that separates our two areas for the purposes of classification, and those classifications generally are saying, so the yellow and red is the prediction, right? That is based on the drawing of the hyperplane. I would classify all points in yellow as 0 and all points in red as 1. Okay, and then the color of the points are the actual points. And so if it's black, that means that it belongs in the yellow, and if it's red, it actually the value of the point is actually 1. Okay, and then the differences between the circle and the X's is that the X's are the support vectors for your hyperplane. Yeah. It's a bit to take in.
Can we add that to the lecture notes?
Yeah. So let me, yeah. So add in description of the SVM plot.
So, I think thinking of the clustering and classification, one thing that you're thinking is that clusters only, I guess, color categorize the existing data points, and this kind of predict the spaces. Like for example, if I say when x1 is equal to -1, x2 is equal to -1, I should be expecting the value of 0. Is that what it means?
So 0, 0, is that what you're saying?
-1.
0 and -1 with here? Or wherever. Anywhere that is yellow, I would predict a value of 0.
Okay, and cluster cannot do something like this.
Yeah, no, clustering doesn't do anything, but what I was talking about is with KNN. So if you guys remember this guy, if you remember our example for classification, right, of that Disney data set about movie ratings, right? This is doing a similar type of thing, and the boundaries here are all drawn based on nearest neighbors, right? And so this is like a different type of thing that is being drawn here, but essentially you're drawing boundaries for where I think values should be red versus where values should be blue versus values should be green, right? And the hyperplane is doing the same thing, right? Except it's got a single separator. Okay. So I will add descriptions of how to interpret the plot in these notes at the end.
So do you want a lot of supporting vectors, like a high value of supporting vectors or a low value of supporting vectors? Or it's kind of just like but the value's not as important, or like.
So the value is not as important as the size of the support vectors. So you want, you basically want this thing that, so imagine that I could like draw the line like this instead. Then you would make the distance between my point and the hyperplane smaller, which is not what you want. You want to, yeah, you want it to be as large as possible, but it gets pushed on both sides, right? Because you've got like a pillar here and you've got a pillar here. So it's trying to balance those as much as possible. Okay. Actually, I think so. We can do our break right now, but actually, I think I'm gonna end a little bit early today, and then for the rest of class, for anyone who's interested, we can do kind of like a review of any material or concepts that folks might be interested in talking about. If you have any like questions that you want me to go back over now that you guys have done homework and taken time to digest material, kind of leaving the rest of today as kind of open for discussion. This can also be in relation to thinking about your projects as well, which I should mention, I'm almost done going through all the proposals. I've got like 3 left, so I will be sending out feedback and commentary on all of the proposals by the end of the day, or end of the night tonight. Yeah.
I was wondering if you could go over time series again and how to control for like time effects.
Okay, sure. We can talk about that. Anyone else have any topics of interest they want to chat about? Oh, why don't we take 5 minutes right now, and then we'll reconvene for anyone who wants to stay, and then I'll take questions, and so we'll look at that. Yeah. Okay.
little confused on the differences between measuring and classification.
Okay.
Is it just the fact that classification is only one point and separate two?
Okay.
Yeah, hold on. It's just like.
I haven't lived out for a long time, but I'm thinking that it sucks.
Yeah, I have notes.
Okay. So this is regression. So we have Y. So this is our explanatory. And so some people will call this dependent variable.
I didn't go to that session. Oh, you did?
And then X is our response slash dependent variable. Or sorry. Sorry, yes. Response. Man, I'm like all over it today.
Very excited when you walked in.
My baby woke up at 3:30 last night. Okay, and so we separate these broadly into Y is continuous, and then Y is discrete. Right, and so we do like linear regression, we've done our like splines slash kernels, and so on. And then here, we did our logistic. We did here LTA, and then K nearest neighbors, and then today we did our SVM. Yeah. So this is in the machine learning world, this is termed as classification, right? Because your Y is like this thing or this thing or this thing, and we're like classifying it into different. So unsupervised, so this is clustering. So no Y variables. So there's no response or dependent variables.
So we're just simply looking at
It's like,
data displayed.
yes, so it's more exploratory. You want to see, are there like things about the data that allow you to group things together on the basis of those things inherently, and not on the basis of those as it relates to like a determined classifier. So these are like very different worlds. Yeah. Does that make sense? Yeah.
Can I see a picture of this?
Yeah, sure. Maybe I'll talk about this really quick to everybody.
Robots is a great movie.
Okay. Maybe a quick breakdown of some of the approaches that we've covered in class. Yeah, because I know we're kind of tackling these things one at a time, and so from a bigger picture perspective, to help clarify things, we've been generally talking about supervised models, right? And then I introduced this concept of unsupervised models last time. And the big difference, right, is that supervised models is where you are basically doing regressions. Where you're looking at relationships between variables, which means that I have information about a response or dependent variable, right, which is our Y. And then we also have information about X's, which are our explanatory or independent variables. And these regression approaches can kind of be split on the basis of the y variables or response variables. We think about this as when our y is continuous, right, versus when our y is discrete. And when y is continuous, you've got things like linear models, the splines and kernels that we're talking about, whereas when y is discrete, then you have like our logistic regression models, the kind of the classic. We also talked about like LDA, linear discriminant analysis, and KNN is a non-parametric approach, and then today are SVMs, right? So all of that falls under y is discrete, and also known as, you may hear this commonly in machine learning lingo, is like a classification problem, right? And that's because our y's are discrete. It's like one thing or another thing or another thing, and we're like classifying based off of our x's what the outcome is. Okay, yeah.
And all of this stuff sort of falls under the predictive umbrella.
No, not necessarily.
Not necessarily.
No,
but
yeah.
linear-
So
I mean, using it in this context, I guess.
yeah, so let me do this then. I'll kind of
Seems like there's 4 quadrants, I guess.
yeah, kind of. Well, so the way that I would it's kind of a spectrum of like where things are kind of more usually for inference versus more usually for prediction. And so let's do box for inference leaning and circle for predictive. And yeah, I guess we can, so what do you guys think? Linear, would that be more inference or more predictive?
Inference.
Yeah, probably more inference, but certainly like common enough that, you could even think about this as like maybe a little bit predictive. And splines and kernels, right? We got no parameters really to deal with. And so this is really going to be solidly in our prediction. Okay, well about logistic? Square or circle?
Leaning predictive, you can use it for inference, you can figure out what the coefficients mean.
I would actually, okay, I get why you say that, because the coefficients themselves are like very confusing, but actually we tend to think about logistic as our like classic inferential classifier. But you're right in that the coefficients are confusing, and so oftentimes I sort of advocate to think about this in probability space, where when you are doing inference, it is a lot more interpretable. Yeah, and so kind of similar type of thing with LDA, and then our KNN and our SVMs are going to be more predictive. Yeah. And then, you have things like GAMs and our elastic net, which are, I would almost say, kind of like hybrid. You can, it is, I would say, developed in a predictive, it was developed in the more school of like predictive methodologies and approaches, but has made kind of has made decent traction in the inferential world. And so you may see things like elastic net or general additive models even in like more classic econometric settings. Yeah, I think that those methods are like now often taught in econometric classes.
I would guess that bridge is probably more predictive and Lasso is more like inference.
Yeah, roughly. No, we just do elastic net these days, so you don't need to worry about that distinction as much. But yes, yeah. And then unsupervised, this is no y variable. This is like completely different from any of this stuff, right? This is we don't really think about these two in kind of the same way. This is going to be more kind of exploratory analysis and getting an understanding of your data, and how certain values within your variables are going to like relate to each other to create these groups. But those groups are not predetermined. We don't know anything about them via some kind of classification that's known. Okay, so yeah, unsupervised is going to be strictly different. Yes.
So in the predictive ones, your X base is meaningful, but not what the X, like you can't, I guess you don't have the like traditional X and Y relationship as you would inferentially, but is there?
No, I would not describe it that way because it is not the fact that the relationship isn't there, right? It is more about how that relationship is kind of described or explained, right? So in the inferential piece, the relationships between x's and y's are simplified or assumed to be simplified in such a way that it's easy to interpret, whereas the relationship between x's and y's is very much present in predictive. It's just that our ability to interpret that in a straightforward way is not really there. And so really what we care about is like leveraging that relationship in some kind of complicated model to get at y's as best as possible, right? Okay. Anything else about this stuff? Great. Okay, so Simon, you want to talk about time series stuff?
How to basically like control for changes of trends over time.
Yes. Okay. So there are two ways that we talked about this, right? Which is differencing and then moving averages. So differencing versus moving average, right? So you've got one way tries to remove trends.
Do you want to share your
Oh, yes, sorry. Okay, here we go. So differencing, you want to remove trends or cyclical components. Where this is smoothing out to reveal underlying trends. And both of these, both of these approaches are doing it in very different ways, but essentially what you're trying to do is to remove, because the whole idea of like time series analysis is to think about there's like a certain variable that you think relates to an outcome, right? But that there's this confounding thing, which is time, right? As time moves forward, it reduces the ability of you to extract the specific effect of like an X on a Y. And so the whole point of time series analysis in these particular approaches is to try and remove that time component that is like confounding your x's effect on y. And it does so in very different ways. One is to like subtract away time trends, and the other one is to smooth out time trends. Does that make sense so far? Yeah.
Makes sense. But I have one question, for example, on differencing, if I like do all the difference, like calculate all the differences, but if I still have like an increasing trend over time, maybe it's some economic thing.
So yeah.
Like what I would thought is that I maybe can add like a time fixed effect, basically. Does that work?
Yes. That is definitely, yes. So time fixed effects is a very common thing to do. You have to be careful, right, about the assumptions in fixed effects of like what things are related to the group, right, and how they relate to your explanatory variables, and you just need to be careful that you're properly controlling for the elements that are extracted by the group. And then so that's probably a more powerful way of dealing with this, but what I will say is that one thing that you're pointing out that you're noticing is that when you do the differencing, it doesn't remove the time trends in totality. And so actually, you can keep differencing. Yeah, and so so it's very common in time series approaches to have several, I forget what it's called, like I think levels of differencing. So you could so if a level of 1 means you're just differencing time 1 and time 2, but you could do a level of 2 or 3 or 4, and you're differencing out, multiple time periods. And the more you difference, the more it removes the trends. And so oftentimes, like, people will difference until the trend is basically flat. And then any of the variation that's happening is, so you basically keep differencing until the mean of the values is flat. And then any variation that's happening is then the like isolated effect.
So basically, if I have the first point in time and the difference with the last point in time, then basically.
Yeah, although every time you add a level of differencing, you are effectively reducing degrees of freedom in your data. So you actually reduce the number of data points, right? Because when you difference 1, you're removing 1 row. When you difference 2, you remove 2 rows. And you can only do that so many times, right, before you.
Can I also difference and then on top of that, like a time fixed effect?
Yes. And in fact, there are so if you look up things like, ARIMA is more on the moving averages thing, but it's doing like autoregressive on top of moving average. So you can like combine different time series methods. You can layer them together. That's pretty common to do. Yeah, we could do a whole course on time series, but I feel like this course is a little bit challenging in that regards because we're kind of sampling from a lot of different things, and there are pieces of this course that you could expand quite a lot into like entire courses. So our discussion of like causality and really focus on the inference piece, that in itself is an entire course at Davis.
Impossible to get into it. So I only have one section.
Yeah. So I'm sorry you're stuck with me and 2 lectures on inference. There's machine learning courses that are gonna dive into basically, what we covered today, SVM, and then over the next couple lectures, some like neural network stuff. That's an entire class right there, right? And so, I kind of think of this class as an introduction to the methods, but more importantly, I think an understanding of the landscape of tools. And then if you want to become a specialist with a particular tool, I would encourage you to to take one of these more in-depth classes to like really, get your bearings. But hopefully this can be a good sort of, intro class to at least understanding what tools are out there and a little bit about how to sort of implement them. Okay. Anything else you guys want to chat about? Any topics you guys want to review? If not, we can always end early. Okay, well, I'll stick around if anyone has any questions for me about anything, homework, projects, whatever. And in the meantime, I guess I'll see you guys. What day is it? I'll see you guys on Wednesday. Mm-hmm.